Are you looking to architect your workloads for resilience on the cloud, but find yourself overwhelmed due to multitude of choices and factors to consider? Well, you're in the right place. In this video, we'll explore some of the key considerations and patterns that can help you make the most optimal decisions for your application's needs. So whether you're a seasoned cloud solutions architect or just starting out on your cloud journey, we will be diving deep into the world of architecting workloads for resilience on the cloud. So, what is resiliency and why does it matter? In order to make sure we are on the same page, let's try to recap the definition of resiliency. Resiliency is the capability of your workload to recover from failure. And failure could take any form. For example, stressed by load, so it could be that more requests are coming in for a service, or the fact that your application is under attack through an accidental bug or through a DDoS attack, for example. Or there could be failures of multiple components that eventually affects your entire workload, right? So essentially, resiliency refers to the capability of your workload to recover from failure. In order to keep it simple, here are 5 core factors you should consider while you're making architecture decisions for meeting your business's resiliency requirements. Throughout this video, we are going to take reference of these 5 core factors and take an example of a corporate banking applications and assess different components of a banking application to design for resiliency. Let me quickly describe what each of these factors mean. For example, while you're making trade-offs on resiliency related decisions on your architecture, consider the design complexity that comes in. An increase in systems complexity typically increases the emergent behaviors of that system, right? For example, you ideally want each individual workload component to be resilient. So you can actually start small by eliminating single points of failures across different factors like people, processes, and then the technology elements. And you're already considering resilience requirements in that case. But if you take it a step further and design resiliency across all your components, it's going to get complex to maintain. The second part would be the cost to implement resiliency. Cost often significantly increases when you're implementing higher resilience because there are new softwares and infrastructure components that you would need to operate as well as maintain. So it's important for such costs to be offsetted by the potential cost for future loss. Just ask yourself this question, that if my application was down for say 10 minutes, what is the cost of the downtime in dollars versus the cost of those 10 minutes? So if your cost for resiliency is higher than the potential business that you're making in case the potential cost for future loss, then you should be weighing out the pros and cons and making the appropriate decisions. Third is about the operational effort. Deploying and supporting highly resilient systems requires complex operational processes, and it only gets complex as your teams are evolving. For example, customers might need to improve their operational processes through, say, an operational readiness approach, which we are not covering as part of this video, but you could have a deeper insight into it on AWS documentation. So, before you decide to implement higher resilience, evaluate your operational competency as well within your teams. Confirm if you have that much level of maturity and skill sets to keep up with that complex design and operational effort needed. And also, is it worth it, right? Further, the effort to secure. Security complexity is less directly correlated with resilience. However, there are generally more components to secure while you're making your systems resilient. And as you get into the nitty gritties of this process, security best practices for cloud deployments will help you keep up with your security objectives and also meet your potential resilience objectives, but then also keeping in mind that you're significantly increasing the complexity of your workload. The last but not the least is the environmental impact that you're making. So, an increased deployment footprint, for example, for resilient systems may increase your consumption of cloud resources, which is directly linked to increased use of, say, potential servers that are just out there waiting for a downtime to occur and then putting itself to use. So you're actually consuming more cloud resources. However, you could use trade offs like, say, approximate computing and deliberately implementing, say, slow response times to reduce resource consumptions. We also have a dedicated video coming soon on well architected sustainability pillar, so where we discuss more about these patterns and guidances for sustainability, so stay tuned for that. Moving on, we're going to take an example of a corporate banking application and try to take some of the components we discussed earlier, the resilience components, and take design decisions upon different parts of this banking application. Okay, to begin with, let's start with the first pattern and let's call it P1, that is the multi-AZ. So P1 is essentially a cloud-based architecture pattern here that we are introducing in terms of availability zones deployed in an AWS region. Okay, so the P1 pattern here is using a multi-AZ setup where applications are operating across multi-AZ but within a single region. So you can see that an EC2 instance is being provisioned in one AZ, but the second AZ has like a backup EC2 instance situation deployed through an autoscaling group. So use case that you can see in this pattern would be internal employee applications, right? Whether an internal employee is trying to look at internal think of is an internal employee's application, okay, which can sustain some amount of downtime, and it doesn't need to have multiple instances deployed because it's eventually a workforce that's trying to consume some of the internal resources. So in case your availability zone fails, the Amazon EC2 prompts an EC2 autoscaling group to recreate the application in another unaffected zone. Worst case, your internal employees might have to wait a little longer in order to access their application, as the EC2 instance is being spun up, which is typically few minutes. Examples of single region and multi-AZ patterns throughout this video. I would like to highlight some of the important topics in order to think about reliability goals. For example, over here you can find example of implementation for availability goals based upon some of the core topics on which you can design for availability. So here you can see that in a single region and multi-AZ setup, you can design for up to 4 nines of availability. Okay, based upon these factors. Similarly, if you want to take your resiliency goals beyond 4 nines, that is, say, 5 nines of availability, there is multi-region design decisions that you need to take. I highly recommend giving the well-architected reliability pillar a read if you want to dive deep into some of the core concepts of reliability. So the second pattern would be P2, that is multi-AZ deployment with static stability. P2 uses multiple instances here, unlike the first example, again deployed across multiple availability zones within a region to increase resilience. This pattern uses a concept called as static stability, and which eventually prevents bimodal behavior. It's different from the first pattern where we saw bimodal behavior in terms of an EC2 instance taking time to spin up in case it needs to be provisioned. Here you can already see two pre-provisioned EC2 instances. And this is exactly what statically stable system means. So static stability requires that your systems remain stable and operate in one mode, okay, irrespective of changes to the operating environment. There are really two concepts here. The first one is your user, while it's interacting with your application where your business logic lies, it is abstracted from the underlying working situation, right? So your users interact with your application through two layers. The first one being the control plane and the second one being the data plane concept. Okay, the control plane consists of all the interaction your user will have with your application, that is create, update, creating and updating your application. All crude operations would be carried out by a user through the control plane. The data plane sole purpose is to provide your business logic, and it really needs a high availability. It needs to be highly available and resilient. And that is the reason why we have to pre-provision resources under the concept of static stability. The key benefit of a statically stable system on AWS would be it reduces complexity of recovery during a disruption thanks to already pre-provisioned resources. So for example, if this AZ is going down, your availability zone health check group will ask it to divert traffic to this AZ, which is healthy. Okay. So again, thinking of the use cases from a banking application perspective would be a customer facing website wherein they require lower tolerance for downtime. You say your banking application or website needs to be highly available. It cannot afford any kind of downtime because it would result in loss of revenue. Because of this, your website say requires a minimum of 2 EC2 instances to be provisioned at any time, whether it's subject to AZ failure or whatever it is, whatever the reason. So that is why this kind of configuration will make sure you meet the typical business requirement, the business resilience requirements to be precise. Again, the trade-off you can see over here is the added cost. Where you need 2 EC2 instances, you're actually deploying for 200% capacity, right? So implementing P2 actually requires your application to support distributed operation across these multiple instances. So you can actually optimize. So if your application can actually support this pattern, where it can support distributed operation across multiple instances, you can deploy your workloads to all the available AZs, usually 3 or more. That's what I would recommend across the region, and say 3 AZs, and then you can deploy for 150% of your capacity across 3 AZs instead of this situation where you have deployed for 200%. That is 2x the capacity. So you save cost and also meet your business continuity requirement, and keep in mind your resiliency goals. Moving on, here you can see that we have another region coming in, that is a multi-region use case. P3 uses a multi-region pattern here, which increases the functional resilience. Disruptions can be abstracted from the user through an alternate regional configuration. The trade-offs here I can think of are P3 mitigates the possibility of a regional service disruption impacting a multitude of systems. I can also think of operating an application portfolio that spans multi-AZs. So region-wide events may still cause disruptions, but the impact surface could be reduced because of isolation of resources from a infrastructure perspective. For most of your use cases, you can achieve your resiliency goals through a single region and multi-AZ setup itself. The next pattern, that is P4, wherein you have multi-AZ, multi-region disaster recovery plan. And you can think of this in terms of four different strategies you can deploy. So pattern 5 would consist of a multi-region active-active situation. And a use case that I can think of where this resilience pattern would need to be used would be, say, a core banking feature like customer relationship management application, where there is zero tolerance for disruption. In this case, the team designing the banking application would need to implement P5 pattern because they would need to deploy these applications with an RTO and RPO of near real time uptime and near zero data loss. The teams would run their workload simultaneously in an active-active situation across multiple regions, allowing them to serve traffic across all the regions simultaneously. This pattern not only mitigates against regional disruptions but also addresses the stringent business requirement of zero tolerance to failure requirement. Talking about the trade offs here, P5 mitigates the disruption at a regional level, but there is a vast amount of investment that an additional cost that goes into uh, implementing the complexity to deliver RTO of near zero. Multi-active deployments are generally complex, and as they include multiple applications to collaborate, you also need to deliver the required business services as is. So far we've seen added complexity, added cost. If you implement this pattern, you'll also need to consider that the fact that you're introducing asynchronous replication of data across regions. So there's an impact on data consistency. Ideally, you would want all of your core banking applications data to be synchronized, like real time synchronized, because you're aiming for an RPO of near zero data loss. Operating this pattern requires a very, very high level of process of maturity in terms of your resilience decision making. So, I would recommend that if you were to build something like this, gradually build towards this pattern. Start with implementing pattern 3, for example, pattern 4, with your making more conscious choices on a multi-AZ and multi-region disaster recovery plan, and then come to the active-active plan. To conclude, I would like to highlight the entire video through this matrix of decision making that will help you make your resiliency goals achievable. These patterns are not mutually exclusive. You may decide to implement a combination of one or more of these patterns and consider the different risks as well as the different complexities and other factors that come in from your decision making on in order to meet your resilience business goals. I hope you found this video useful. If you did, please give it a thumbs up and do subscribe. Thanks.